Kinematics in one dimension summary. We'll start with some definitions. On the left-hand side here, over here, we have our definitions. These equations are valid in all cases. We start with the average velocity and average acceleration, and you represent average by a bar over the variable, and that's the change in position over change in time, and then the change in velocity over change in time for acceleration. Then to find the instantaneous velocity and instantaneous acceleration, we take derivatives as shown. Now here's a very handy equation, but there's a limit to it. You can only use this equation where the acceleration in your problem is constant, and that's the average velocity equals your initial velocity plus the final and divide by 2. Here are the big three equations, first, second, and third kinematics. The first one, velocity is initial velocity plus AT, but before we go on, let's look at the caution down here. Just like the average velocity on the previous page, these equations, they were all derived assuming a constant acceleration, so they can only be used in cases where you have a constant acceleration. And then here's our second one, that's the position equation. And then the third one. What do you notice different about this third one than the first two? Yep, there's no time in it, and it was actually found by using a combination of the first and second kinematics equation, so it's really not a separate one. But this can be very valuable, so if you ever have a problem and there's no time given or you can't solve for it, look for the third kinematics equation. What if we have a problem where the acceleration is not constant? Well, we know we can't use the three kinematics equations. What can we use? Calculus. And what we're showing here is we can find the velocity if we're given position as a function of time, and we can find the acceleration if the velocity is a function of time. And of course, if we know position, we can take the first derivative to get velocity, then take the second derivative to get acceleration. What if we're giving the acceleration and we need to find the velocity, or given the velocity and we're asked to find the position? Well, instead of differentiation, we use integration. So to make the problem solvable here, we'll assume an initial position of x0, initial velocity of v0, and we'll set time 0 equal to 0, unless of course the problem specifies otherwise. So we can find velocity by our initial velocity plus the integral from 0 to t of the acceleration dt. And then position is found by integrating velocity and adding the initial condition of x0. So here's a handy little mnemonic. If we're given position x and we want to find velocity or acceleration, we go down this way with the derivatives. So velocity is dx dt, acceleration is dv dt. If we're given a and we want to go in the other direction, you integrate it once to get velocity, and be sure to add the initial velocity here, and you go one more step to find the position, and that's an initial position. Now other times you might be solving in certain intervals, so the 0t becomes something like, we'll just put a couple numbers here, from 1 to 2, or 3 to 4, whatever number you have. And in that case, you don't need the initial condition. Okay, you're going to take care of that with the definite integral. Common problems will show you a graph of position versus time, and you call those position time graphs. Okay, here's position on the y-axis, time on the x, and we have 5 points labeled here, A, B, C, D, and E. And actually down here, it seems like we went into negative time, so we'd like to shift this up a little bit. But let's look at the 5 points. A is not at the bottom of your curve here. It's actually on right at the end of the curve, okay? So it has a positive slope, and it's part of the shape here being concave in the up direction. So let's erase that so you can see it again. B will be on the straight line of the curve. That's a straight line. C is at the peak of the curve. D will be on the straight line again. And E will be on a curve that's concave up. So what does that mean for velocity and acceleration? Well, we have the table over here, and on the position time graph, point A, it's positive slope, and it's concave up. So you may have seen this in your calculus class when you did graphical analysis, or maybe you haven't gotten to it yet, so you're seeing it here for the first time. The slope of the line is positive, so the slope of the line on a position time curve, well, that's dx dt, and that is the velocity. So the velocity will be greater than 0, and since it's in the concave up position, that means the acceleration is greater than 0. And the particle will be moving in the positive x direction and speeding up, because the acceleration is in the same direction as the velocity. Point B, we're on a straight line, 0 curvature. Once again, our velocity is 0. You have a positive slope there at point B. And the acceleration this time will be 0. There is no curvature. So you're moving in the plus x direction and no change in speed. We get up to point C. 0 slope there. So that means your velocity is 0, and your acceleration, since you're concave down, will be less than 0. You are instantaneously at rest here, and your velocity is changing from positive to negative, which explains the negative acceleration. So let me just erase some of this as we finish with D and E. D, you have a negative slope. You're on a straight line, so you have 0 curvature. So your velocity is less than 0. You have 0 acceleration. Your particle is now moving in the negative x direction and no change in speed. Finally, point E. Negative slope still, and it's concave up. So in that case, our acceleration is greater than 0. The velocity is less than 0. And you are moving in the negative x direction and slowing down, because your velocity and your acceleration are in opposite directions. Summarizing what we just showed on the previous graph, the slope of the curve on a position time graph, otherwise known as the first derivative, that gives us the velocity. Positive slope, positive velocity. Negative slope, negative velocity. The concavity, that represents your second derivative. And again, in this case, that would be acceleration. So concave up, acceleration greater than 0. Concave down, acceleration is less than 0. And if you have 0 curvature, your acceleration equals 0, because the second derivative would be 0. And I don't know, a mnemonic to remember these, you could go through the math and figure it out, or concave up, that's a happy smiley face, so you would assume that the acceleration is positive and happy, so it's greater than 0. And I apologize for the mnemonic.